Hi all, this is the second video about turbulence and its modeling. So in this video we see about a brief review about how the transition from the laminar, like a stable laminar flow to unstable turbulent flow, happens based on hydrodynamic instability theory. So though we are not going to go that deep enough, just we'll give a brief overall understandability what hydrodynamic instability theory says about the transition from laminar flow to turbulent flow. So the crux of the theory is something laminar flows subjected to perturbations in their flow equations. So if it is subject in terms of physics, it's subject to a small disturbance. How this disturbance happening in uh, over the period of time. If these disturbance are attenuated, then the flow remains laminar and the stability maintains. But if there is an amplification to the small disturbance introduced while during the stable laminar flow, these amplifications causes that typical critical conditions called a critical Reynolds number, at which these disturbances are getting amplified beyond certain amplifications, and there happens a transition to a fully turbulent flow. So these theories are have a very rich mathematical structure, which is beyond this these limitations in this video. And like a comprehensive overview of this theory has been given by White in this paper in 1991, and is mainly this theory is about a simple two-dimensional incompressible flows, like flow over flat boundary flat plate, flow through a jet, and flow through a pipe. So there are two basic things how the boundary layer is developed along the flow direction, transition to the flow directions. If there is a point of inflections, then this if there is no point of inflection, these are the two main criteria how the theory is built upon. If there is a point, if the flow distributions has a point of inflection, this theory is based on inviscid assumptions. There is no viscous effect plays a great role here, and even if there is an viscosity is introduced, it doesn't makes it to make it stable, doesn't usually happen. So if there is an introduction of the viscosity, it makes the flow to become stable. But if the viscous effects are very negligible, and if the inertial is are very predominant, that is the things of high Reynolds number, this inviscid instability theory applies, and it says that there is a principal evolution of the amplification of the small disturbance introduced at the beginning. So this amplification is mainly happening similar to flows where there is a adverse pressure gradient. So the role of here the viscosity is to dampen out the fluctuation and makes the flow to become stabilized once the Reynolds number is reduced. So the another theory is something like, even if there is irrespective of the viscous effect, there occurs instability, and that instability is termed as an viscous instability. So even this happens without any an adverse pressure gradient. And that these mainly something like, even at high Reynolds number there is stable flows, and even at a small Reynolds number there is stable flows. That the damping effect is happening because of the predominant effect of the viscosity. But there is an intermediate critical Reynolds number where this instability happens. So first we come that related to the inviscid instability, and there two Reynolds numbers are defined. One is critical Reynolds number and transition. Critical number is the one where the small amplifications of the small disturbance get predominantly gone beyond that certain limit. And once after that stage is crossed, there occurs another transition Reynolds number, at which this amplifications grow into a instability during that and becomes a fully turbulent flows. There are different types of flows happening. One is we describe as the first example is a jet flow. This belongs to an inviscid instability theory, and where there is a point of inflections along the flow distributions happens. So here initially the flow is laminar. Once the flow comes out of the jet, vortex is rolled up, and further downstream these vortex are get amalgamated and vortex pairing happens, and further downstream this mixing of this vortex happens, and this and the flow breaks occurs, and it becomes a fully turbulent flow. Then the second example is boundary over on a flat plate. This also this belongs to a flow without a point of inflections, and this happens occur at a finite this in previous one happens at a Reynolds number of 10. Here the Reynolds number of around 100, that infinitesimal disturbance are getting amplified, and there occur initially these are the flow process happens. So initially the flows are here, then there is occurs some kind of an instability of waves which has a long wavelength along the principal directions happens, and further downstream if there amplification there are two conditions: either the amplification can be attenuated, or if that in sense the amplifications are amplified, the amplitudes are amplified, then there occurs certain kind of called as like vortices, like hairpin vortices occur. These hairpin vortices further going downstream have a clear pattern like kind of called as K-type vortices. This clay-type vortices further then that can be as similar to the previous one. There will be some merging of this vortices, and then becomes a fully turbulent flow. So these things happens around at Reynolds number. This transition happens around at 10 power 6, and criticals happens at 1000. Now the pipe flow transmission, this has doesn't have as similar as earlier flow types like jet or flow over a boundary plate. This theory is not well defined for the reason that they couldn't able to understand, because as per the theoretical point of view, the introduction of viscosity makes this flow to be stable at any infinitely large Reynolds number. But however, in practical conditions, that instability occurs around the Reynolds number of 2000 and becomes fully turbulent around 10 power 5. So the one of the failure of the theory is mainly to understand the reason would be related to the initial uncertainty in the entry effect. That is because of the distortions in the initial velocity profile, and also there occurs not a small disturbance, a finite amplitude disturbance occur on the entrance of the things. So because of this, there occurs some turbulent spot in the near wall region. While going up, there occurs a kind of a turbulent slug across the cross section of the pipes. So there will be an alternative of laminar and turbulent flow around the Reynolds number of 2000. But once the Reynolds number crosses 2000, there will be a mixing of the slugs of turbulent flow, and this mixing causes to become a fully turbulent flow in the pipe region. So final comments about this hydrodynamic instability theory is about like an amplification of the small disturbance and development of the rotational structures downstream because of these amplifications, and there will be some kind of a small scale motions because of this merging of these rotational structures, and this merging causes to form a small scale motion which is further developed into a fully turbulent flows. So this transition to turbulence is caused because of this adverse pressure gradient and wall roughness, the entry effects, and heat transfer in the subsonic flows. There is no any big comprehensive theory for the compressible turbulent flows, and moreover, these theories are based only upon the very simplistic geometries. We are the comprehensive theory of the complicated things are still missing here. So the theories are well developed for external wall boundary flows, but when it comes to pipe flow, it's not that well developed, and there are some commercial CFD procedures are being developed, ignoring completely these transitions and classifications. Okay, hopefully we coming into the next video about the computational point of view of the turbulent flow modeling, and for that we need to understand about what is time averaging, and how that time averaging effect developed into a Reynolds equation called time average Navier-Stokes equation. Hopefully we'll see that in the next video. Thank you.